just realized that y'all were getting blasted with music louder than usual. My bad for that. I am very, very out of order this night. As usual, I decide to, I don't know, faff about for too long, and then I, don't have time to properly get everything going on stream, and now everything's kind of crashing into each other, pun not intended, and we're just, oh my god, it's a mess, it's a disaster. Oh no, stream is ruined. It's not that bad, but it's still, like, kinda, it's things that don't quite work, like how there's still credits for a song that's not playing on screen, or starting the stream with, like, the regular stream layout going there. It's being one of those days right now. So, yeah, that's, it sucks, but welcome. We're here for science. I will also say happy quote-unquote Trans Day of Remembrance. It's not exactly the, it is a grim reminder of those we have lost to bigotry, but also a call to action to keep going and show our friends love, regardless of how they identify and how their brain works and all that stuff. I have trans friends, and I certainly don't want to see them go anytime soon. I support them, well, as much as I can. We don't talk often, just by the way of how life goes, but, I like to check them out every once in a while, Check in on your friends. Be sure to do so. Alright, well, with that, I guess I should just make a last-second check here to actually make sure everything I'm doing is in order. Because, I mean, yeah, how much I rush to actually get things together here, that could be wrong. Okay, so I have my paint.net up, I have my notes of things I could talk about, I have the video here, I have an explainer for the video in case I forget how to explain things. Just check and make sure that that explainer is easy to show, not going to show anything personal. Okay, good. Ooh, very laggy display right now for some reason. That's not reassuring. Maybe I should disable the OBS preview. Maybe things will start running a little better. Yeah, that's good. Okay. Alright. Hey, here we are. Let me get on with some things. We're currently listening to the stream background playlist. If you're actually interested in any of the things that I've been playing, then I do have a playlist on my channel. It's public. You can go and take a look at it. What I like to jam out to while we're on stream. But today we're going to be starting, not with our, title video. We're going to be easing into things as we did last week. I didn't get a chance to talk about periodic video. Oh, hey, that's me. Why am I on my own playlist? That doesn't sound right. I didn't get a chance to watch anything periodic videos last week, just because the videos got a little bit long, and, they are a little bit of a drier sort of video. They're a little bit more on the entertainment and a little bit of British humor kind of side of things, so it tends very, very dry, professional British humor. But, I think that what they do is fascinating, and so I like to watch them every once in a while. And, what's even greater, too, is they're often accessible, so for people who are not, like, super chemistry literate or an expert in chemistry, you can usually watch their stuff and glean stuff from it, because it's meant for to be accessible to specifically for undergraduate chemists. But that's pretty introductory level chemistry as well. So let me pause that music over here, and then we can actually get to it, right? All right, making sure the capture's working. The capture is working. PNGTuber Maker is not working already. That's pretty bad. All right, testing. Okay, there we go. All right, cool. So first video is from Periodic Videos. They talked about the Nobel Prize in Chemistry of 2025, which I believe happened 2 months ago. I don't really keep track of exactly when the Nobel Prizes are handed out. I'm kind of bad on that aspect of things. But it should be an interesting topic. It talks about a I already know what it is because I've heard other people talk about it, but it basically talks about what are known as MOFs, M-O-Fs. I might as well write that down. This stands for Metal Organic Frameworks. I can use the typing tool to help that out a little bit more. Metal Organic Frameworks. and they are pretty similar to what they sound like. They are a combination of they are structures that are built off of metal clusters. So you have some kind of metal in the middle. Hold on. That's not my drawing implement. So you have some kind of metal ion in the middle, and you have let me draw a good circle here. A decent circle. That's good enough. You have other things, the organic component. So I will represent that as that's a good way to do this. I'll just draw an actual example of some kind. So let's do a squiggly line to kind of represent the rest of a structure. And you can have something like this would be an acetate group, 2 oxygens, a carbon, and another oxygen with a negative charge, binding in to the metal, forming a somewhat ionic, somewhat covalent bond. And this structure can repeat in multiple directions. Doing like this. And so you end up with something that basically looks like this on the larger scale. So you have your dots kind of representing your metals, being like the points that the scaffolding is being built off of, and the organic parts being the scaffolding building out a framework. And what is particularly interesting about these is that you can kind of tell as I'm drawing. Usually you see a drawing like this of, like, say, a salt like sodium chloride, and that the space in between the atoms is kind of exaggerated to actually just make the picture a little bit clearer. The atoms are not actually separated that far apart. Hold on. I have perspective issues here. But the cool thing with MOFs is that they actually are porous. Like this, these holes in the structure actually are large enough to fit molecules through them. Usually just very small molecules, but molecules nonetheless. And so you end up having a material that is low density, porous, and has sites that can do catalytic chemistry. So sites for chem. I think I'm going to be talking about a little bit more MOFs here, so let me turn the music back on. I didn't think I'd be preambling for this long, but I am, because MOFs make me kind of excited. They're one of my favorite things from chemistry. But yeah, so you end up getting material that's low density, porous, has sites for chemistry to happen, and importantly is also modular. It's not a completely trivial thing to just swap out one metal for another at one of these points. The structure is going to change a little bit based on atomic size and how compatible the metal is with the ligands and how well they're going to bind together. I guess I should also write down these are called ligands. Ooh, okay, that's lag. Why is that lag? Hopefully that writes out correctly. Why is that lagging so badly? Oh my god. But yeah, and what was I saying here? You can fairly easily swap out different metals, different ligands, and so you can get, if you use a longer ligand, you can get a bigger cage structure. You can have more pores, although there's issues with stability at a certain point with that, but you can push it. If you change out the metal site, you can do different chemistry with it. You can maybe even change the geometry, because some metals like to be in kind of a, 6-coordinate arrangement where it's at the center of like a cube, kind of like how I've drawn this one here. Or it might want to be at the corner of a tetrahedron, and so it branches off in 4 directions instead, and you get different cavity sizes and cavity shapes as a result. The point is that you can do a hell of a lot with these materials. They are fairly simple to make, and they offer unique chemistry that does not easily present itself in a lot of other catalysts or solid compounds. And, as a result, Nobel Prize, after enough decades just percolating in the scientific mindset. It's pretty worthy of a Nobel Prize, in my opinion. It kind of kickstarted an entire new branch of chemistry for people to sink their teeth in, and is, I won't say the fundament for organometallic chemistry, but it makes a basis for a subset of organometallic chemistry. You actually get the chance to rather than just being metal organic compounds that are lone floating chemicals, they are solid materials you could work with, modify them, all that good stuff. I love MOFs. That was one of the most fascinating things that I had learned about when I was initially getting into chemistry as an undergraduate myself. So yeah, this stuff is great. So now that I've done my preamble, we can actually get to the video on said compounds. All right. Let's make sure everything's working. Please. Make it a little louder.
This year's Nobel Prize is quite exciting, but not unexpected.
Watch the broadcast. I usually like tuning in and just trying to guess what it's going to be as they sort of start teasing the clues at the beginning of the announcements.
To award the 2025 Nobel Prize in Chemistry to Susumu Kitagawa, Kyoto University, Japan; Richard Robson, University of Melbourne, Australia; and Omar Yagi, University of California at Berkeley, USA.
Before
Extremely minor fact, I have cited Omar Yagi for things before in not actual publications, but, schoolwork. And it was, it's funny, I can actually recognize one of the names receiving the Nobel Prize. I usually can't do that.
the ceremony was completely finished, I realized that two of my younger colleagues, Ben Pilgrim and Matt Cliff, worked in this area. So I rushed off to find them to see if they had some nice samples of MOFs and perhaps some models to explain
lo and behold,
the chemistry.
Any chemist working with MOFs definitely has.
Sometimes I watch it live, but this time I had to have a meeting with one of the technical staff, and then I was talking with her in the corridor, and Martin came around the corner, basically looking for me because the Nobel Prize, of course, this year was in MOFs, which is what I work on.
Having to miss a Nobel Prize in your own field for a
meeting of a new
sucks.
Class of compounds, so-called MOFs, metal organic frameworks.
They're a repeating structure held up of sort of two components. The metals are almost like the glue that kind of hold the components together.
Yeah.
And then the organic components, they're sort of these kind of rigid linkers that bridge between different metal ions. And what's different about these to other sorts of structures is how open they are.
The Nobel.
Something funny is that, he mentioned that the linkers, the ligands are actually really rigid. And most of the time this is true. Like, people tend to design ligands that are fairly like straightforward, that aren't going to bend and twist too much, because that cage structure is not going to be very stable if it wants to collapse in on itself. So you might see something that kind of gets designed more like this, where it's like, okay, this turns into a phenyl group, like so. Oops. I'm very out of hexagon drawing practice. This is like a phenyl group, and let's put another one in there to kind of make some extra space. Draw that. And then you have another one on this side, another acetate group on this side, just so that way it, binds to another metal. You might get something like this. This is a nice rigid structure. And so this is going to actually hold up that like cage structure pretty well, all things considered, if you pick the right metal to go along with it. You just redraw the cage to emphasize the point, then you just draw the cage a little better. Okay, good enough, I guess. So you're gonna get, actual cage structure that's nice and ordered. It's gonna repeat itself multiple times. However, it is possible to actually make amorphous forms that is more glassy forms of moths if you actually use more flexible ligands. So you could have, for instance, a similar material, and I'm not sure if this is like one that exactly works, but instead of having phenyl groups in the middle, you could have pretty flexible, just a carbon alkane backbone. So all of those points are just various carbon atoms with their hydrogens on them. And then they could link up much like glass in kind of a somewhat random order, where you have just things going in whatever directions. I'm just kind of trying to draw randomly here. I don't want multiple going there. Maybe I do. Yeah, maybe I do, because they are going to still connect multiply in different dimensions. And the spacing is supposed to be more equal, but, I can only do so much with my hands. Yeah, and so they kind of just start to cross over and stack on top of each other. And fundamentally, that's what just a glass is, some kind of solid that is has no regular repeating structure to it, and as a result ends up just being kind of a wibbly wobbly mess of various atoms, but it's still strong enough to kind of keep itself together rather than just completely fall apart into separate molecules. And there are a couple of linkers that can get you an amorphous shaped moth, which, it kind of just makes the pore size random, and maybe not all the centers are available for chemistry, but there are some distinct advantages. Like if transparency is an issue, then this tends to help. Or if the material properties are much better, because something rigid like this could easily kind of just be smashed. Like they tend to be brittle because of it doesn't have flexibility. But something like this is, well, it's spaghetti. It's like, I mean, if you ever take a hammer to glass and it shatters, well, okay, that's actually a terrible example given what I'm talking about. If you take like a hammer to some like a big rock of limestone, it'll shatter when you hit it with that hammer. If you hit a big plate of spaghetti, it's not going to shatter. Now, I might as well also bring up the fact that I just said that if you hit a glass with a hammer, it will shatter. So why is the glass shatter if it's supposed to be like spaghetti? Well, that's because if it's not warm enough, then the spaghetti acts like, dry spaghetti. And so if you hit frozen spaghetti with a hammer, yeah, it would probably shatter. If you hit warm spaghetti with a hammer, it wouldn't. And glass has to be really, really warm to not shatter if hit with a hammer, let's say.
Prize presenters or the committee members talked about it like Hermione's handbag in Harry Potter.
Small on the outside, but very, very large on the inside.
I've never read Harry Potter, so I don't know whether that's a good analogy.
Do you know the TARDIS in Doctor Who?
Yes.
It's like that too.
Yes.
Yeah.
You can think of it a bit like a kind of like climbing frame, where the sort of joints, so the rods of the climbing frame are organic molecules, and like the joints connecting them with the metal atoms. So it's a kind of self-assembled.
Yeah, you can see
typically crystalline.
You can just see the variety of different like shapes within like moths. The variety of different shapes you can get in the classification of molecules as moths. Like you can have each of these blue kind of polyhedra represents one of those like metal clusters in the middle, and then you have all of the other ligands linking things in between each other. And depending on what the metal is, how the metal clusters organize themselves, you can get things that like in the upper right, that UIO67 has triangular symmetry between all of the nodes connecting to each other. You could have something with hexagonal symmetry, like the NU1501 in the bottom right. You can have different forms of hexagonal symmetry, like with this ZIF8 in the bottom left, or you can have layered things like MOF303. And, again, possibilities on possibilities on possibilities.
So it's a kind of self-assembled, typically crystalline and not always material.
So this model is kind of showing the general structure of a moth. So made out of metal here, these metal balls are actually where we would have our metal ions or clusters in the moth, and then these coloured rods there, or organic components, they're the linkers that link them together.
So those rods between the metals, that's not representing bonds. They are actually...
That's a whole molecule, a whole series of atoms linking these two together. In terms of the metals, they've been used, across the whole variety of the periodic table. There's moths made from all of them, but
sash automatically closing the... Hold on, what?
I'm
I'm sorry. I got distracted. There's like a ghost sash in the background there.
All of them.
It's just falling on its own. No one's doing that. Maybe in England they have fancy automated sashes where they detect it's not in use and it falls down, but I've never seen something like that. I'm probably guessing it's just actually kind of like faulty. You can witness a fume hood crapping out in real time and requiring maintenance.
The periodic table, there's moths made from all of them, but ones like, for example, zinc, iron, some of the ones you'd have commonly heard of are used a lot just because, again, they're cheap and easy to access. In terms of the linkers, again...
Nothing screams a useful chemical compound like low cost.
There's a whole variety, any kind of shape and size you want. In terms of the what we call the functional group, so what's at the end of the linker attached to the metal, quite often that's something called a carboxylate.
Hey, Dakota.
That's a group with a carbon
Sounds cool.
and 2 oxygens. It's got a negative charge.
Happy to have you lurking.
Quite strong ionic connections to the metal that help kind of keep the structure together. But as I say, the real thing that separates these materials out from other types of materials is their porosity, their open space. So it can be, up to perhaps 90% of...
Oh yeah, I guess I could also mention, like, I think he was kind of getting into this, but with, like, the functional group talk, go back to, like, our picture of ligands here. Like, I could theoretically have drawn this differently. I mean, usually you're not going to get catalytic activity at the, along the actual carbon organic linker here, but in case you needed something to say maybe assist the metal, this could have like an amine group on the end of it that could maybe help fasten whatever organic thing that is coming in and needs to interact with like a metal that's over here. And it's like, oh look, something could bond in, and it's like, oh look, bonding to that, hooray, it's working. So yeah, you can also do a lot of stuff with, like, not only can you modify what metal you're using and what ligand you're using, but then you can also modify the ligand further to see if it has any extra groups that'll do interesting chemistry with it. Again, these are an amazing class of materials that you can play with to your heart's content if you have enough money in chemistry knowledge.
Volume within a moth is actually empty space. That's huge compared to a lot of typical materials where only a small percentage is empty space. And then shown in this model, these little water molecules, not really to scale, but this is just to kind of show you the concept that
they are cute little buggers,
molecules, maybe it's water, maybe it's carbon dioxide, can pass freely through the pores of this structure, maybe adsorb into the interior. So this was a material that was going to help sequester water from the atmosphere.
Richard Robson, who is in Australia, who was the first person who had the idea of making these materials. He was inspired by the structure of diamond, which has a regular arrangement of carbon atoms, and wondered whether he could make an organic and metal compound with metal ions and organic groups, which had the same
it's actually cool.
structure, but much bigger spaces between them.
When we heard the Nobel Prize, we went to the lab to try and grab some to see what we had in the stock, basically. This is nickel dichloride 213 benzothiazole, nickel BTD. This is an iron 2.
You're going to show me a structure of that? Because even I'm a chemist, but I can't come up with...
less colourful manganese.
I can't recognize exactly what that structure is off the top of my head.
Related. We have a less colourful manganese material here. This is manganese triazolate. So we've got, these are relatively large amounts of materials that we'd make, and we made these ones for magnetic studies, for neutron diffraction studies.
Robson's work was done a long time ago, in the 1980s.
I don't know enough about neutron diffraction to comment on other fact that if you make the pore size of these moths the appropriate size, then it can act as a diffraction grating for neutrons, and so you can take images using of really small structures using neutrons. But that's kind of as far as my knowledge goes.
After that, Sasuma Kitagawa in Japan made conceptually similar structures, but Robson had ions, nitrates or whatever, in the gaps in the structure. Kitagawa had water molecules which, when you heated up the material, could come out, so you were left with a much freer structure where other molecules could go in.
But we've got some classic materials, so this one is UA66 amino.
What's in that one? Has that got uranium?
No, oh yeah, okay. We've stumbled across one of the fun things, or not terribly fun things, about moth chemistry, which is that because they're relatively
I'd also say the cameraman Brady, he is not. He's distinctly not a chemist. He is a videographer by nature. So it's fun having him kind of insert his commentary where he gets concerned about things when it's like a normal chemist would not just completely brush it aside, not even think about it. But he's great on this channel as a result, because like it's meant to be an educational channel. He's kind of like your most relatable for those without chemistry knowledge.
Things, or not terribly fun things, about moth chemistry, which is that because they're relatively complex in terms of the composition, they've all got sort of official nicknames. So UAO is the Norwegian for University of Oslo, and it's a 66 material. ZIF8 is just zeolitic imidazolate framework, so it's another chemical name. It's zirconium.
That's zirconium.
Yeah,
and
zirconium.
that U stands for university.
Yes.
The third recipient,
confusing.
You remember only 3 people can win a prize, was Omar Yagi, who's originally from Jordan and now works at University of California in Berkeley, who has made a vast range of different moths. It is his group that made the compounds that...
I've seen these diagrams so many times in my life when I was studying in undergrad. These are like textbook, literally textbook images to get this concept across.
That can take water from the air and supply drinking water, which by chance we described a week ago in our video about dysprosium. And there's groups in California.
Don't spoil it. I'm
going
to eventually react to that video later.
Make emergency water supplies for travelers, for soldiers in the field, using compounds that will attract water from the air. We were right on the ball.
But actually, that does bring up a good point of like what an application of one of these could be. So, as mentioned, it's like, yeah, you can have, I'm going to do my best to sketch this out quickly. You can have a moth that, due to chemical composition, ends up being very good at soaking up water. And so you can essentially make a desiccant out of a very effective desiccant out of these structures, because it, unlike conventional desiccants, there is all this empty space inside of the structure. And so it can actually absorb theoretically a lot more of water from the atmosphere. And not only that, while this is a feature of some desiccants, not all can really claim this feature. It can be done reversibly, in the sense that you can actually heat them off up to a certain temperature, and it'll release the water back out into the atmosphere when you want it to be released. And, some moths can, or some desiccants can do this, but it comes with a breakdown of the structure, or some can't do it at all because it absorbs water from the atmosphere by simply like incorporating it into its structure irreversibly. But the great thing with this is that, like, yeah, you can get that water back and then you can reuse the desiccant, and it's great. And it's a really interesting kind of like fusion of ideas, because these are components alone, like the metal and the organic framework, like are not really um, poised to absorb water on their own. But when you make a full structure like this, you tune the chemistry, it'll actually take up the water in the first place, and then you can start doing stuff with it. And you know, I just think that's neat. I had one other point I was gonna make. What was I going to say again? Um, takes up the water, re-releases it. Oh yeah, and then so there is also the issue of like some time. Oh wait, no, hold on. The other thing I was going to say is that when you combine these components, like you get that reversibility of the water leaving and coming back as well, because this structure in total ends up being pretty heat resistant when maybe the individual organic components would be, boiling or burning at that like 300 degrees Celsius, which you might need to get the water off. Or maybe less, maybe say 200 Celsius would be, generous for it. And the metals don't melt until like 3000 Celsius. But you have these together, the properties kind of combine. They don't really average out. It's not how science works, but the properties of the new material are such that it is heat resistant enough to be able to take on heat, which causes the water molecules to dispel, and then you can have it absorb more water again. You can reuse it. It's fundamentally amazing chemistry technology.
All for this year's Nobel Prize.
It's great.
And I should also say, furthermore, like this has been repeatedly investigated to some avail of trying to do carbon dioxide capture to help combat climate change. And it works. It's hard to do, mostly because carbon dioxide just does not really like binding to things for the most part. It's a fairly inert gas, not completely, but mostly inert. And the moths that do pick it up, well, that tends to be ones that pick it up really like permanently, kind of like this, as I was describing with some desiccators, where it's like it picks up desiccators that pick up water too well, incorporate the water into the structure too well, are very hard to get the water back off. Similarly, we have a lot of moths that are able to pick up carbon dioxide from the air, but usually only once, because when they bind into the sites in the moth, they tend to not be able to be easily removed with a modest amount of heat, or the heat that you have to apply causes the entire thing to collapse and burn up. So it's an ongoing field of research, but it's pretty difficult to do.
From the air, we were right on the ball for this year's Nobel Prize.
It's great news. I mean, already moths is a huge field. I think what would be good is for moths to make real headway in terms of commercial applications on a large scale. So whether that's in bulk
that would be nice.
Materials for CO2 capture, water harvesting, maybe water purification.
I have been involved a small amount in making moths, not making original compounds, but scaling them up in flow systems. And my colleague Ed Lester in chemical engineering has created a company, and they're now a major manufacturer of moths. And if we're lucky,
Cool.
they'll show you a sample.
This is almost a world exclusive. This is our brand new rig that we call Matisse. So moth adsorption test rig informing scaled up.
Man, that is, I've never done chemistry at this kind of scale. It's really kind of fun when you actually see chemistry, that like the practical engineering ends that go into taking chemistry from the bench where you can just do everything by hand to this is an industrial manufacturing unit. It's automated chemistry. It flows through. You need big steel containers. I don't know. It's a feat of engineering. I love it.
Engineering. And basically, it's a system that allows us to take the moths, allows us to flow gases through that, like a simulated flue gas from an energy plant. And the moth will strip out the CO2 and then leave behind that a kind of cleaned up flue gas that we'll be able to use for all kinds of different things. So the moths would be in each one of these columns. So you would see here, this is where the moth would be. We'd flow the gas all the way through the bottom. The moth would trap the carbon dioxide. The cleaned up flue gas would come out the top, and then in this particular model, we would vent it. But then once that MOF gets saturated, it's basically a cycling process. We'd move over to the next column. Once that one gets saturated, we would have regenerated this one and removed the pure CO2. And then basically we switch between columns left, right, and center.
And in this particular case,
They have something mildly efficient at actually removing carbon dioxide. Of course, they haven't managed to sell this. They're just doing a test on their own. But hey, you know, the thing I was just talking about and selling and hyping up, it's real.
the MOF's almost like a sponge filter that you're stuffing in the chimney.
Yeah, exactly. I think that's the best way to think about them, as little sponges or sieves. You know, the work that the inventors of MOFs did, like Omar Yagi and people like that, you know, what they did was basically create these structures with metal ions at the corner and then organic linkers. These create almost tuned pores or holes that are just the right size for a gas molecule, like a carbon dioxide, such that it would trap that molecule and let the other ones pass through. And you can see almost immediately, as soon as we started flowing it through the MOF, you see that CO2 concentration drop down to almost zero. These
Very
are the ones
impressive,
that are actually in
actually.
the system right now. So these
purple.
are what the particles look like. I mean, there's still a lot of work that needs to be done to optimize the shape and the form of these, whether it needs to be a fine powder or whatever that size particle needs to be. That's what the system designers and the chemical engineers over time will all figure out to make that more of an optimized system.
It's one of those areas that's kind
I was gonna say, with the purple pebbles you can see there, it's kind of important to remember that, like, while I have been describing these as porous materials, like, they still realistically are, like, pores on the size of, like, nanometers. It's not, unfortunately, the material itself doesn't, like, just look spongy from a distance. It just is kind of internally a little spongy.
of very big in sort of chemistry. Like, you know, most chemistry departments will have a group or two working on metal organic frameworks nowadays, but it hasn't, I think, fully crossed over to the public consciousness, because they are, you know, really only, you know, depending on how you define it, only really about 30 years old, and they haven't got the same kind of the big application that you wouldn't find a MOF in, like your in your house probably.
The key point about the
Specialty
discovery by
applications
these,
currently.
all three scientists, is not so much the materials they made, but they opened up the principle so almost anybody could make a MOF.
Yeah, so here's just a couple of different examples of the MOFs that we produce. So here you can see one which is very similar to what's in the carbon capture rig that we showed you previously. So you can see the pellets here, slightly different form to what we had in the last demonstration. So that's one particular MOF where you can see.
That is crazy for me. I've never seen a MOF actually produced at that scale before. Usually they tend to be like 50% yield syntheses on like a lab bench, but to see them like in these extruded pellets like this is, I don't know, that's fun for me.
Probably around 25 kilos here. So it's interesting that people in the MOF world are still mainly talking about grams, maybe kilograms, right? We're already at the ton scale. So we just recently completed an order whereby, you know, we just sent 4 tons of material to a customer for a gas storage application, as an example.
Wow, goddamn.
We've got a completely different MOF, completely different metals, different
like
linker
chalk.
molecules, but it allows us to use different MOFs for the different exciting applications that we're working on. Carbon capture, water harvesting, gas storage, biogas upgrading, you know, pretty important energy sensitive applications where we're going to make a big difference in decarbonization and what the world has been challenged with. We've got good capability to make hundreds of tons to satisfy customer demand over the next couple of years, but we're using some of the investment money that we recently took on to expand our capability and move into future facilities that allow us to continue to grow with that demand.
Of the 3 Nobel Prize winners,
I also tend to like MOFs too, just like as I keep harping on this environmental thing, like it's actually not like a horrible application. Like it's kind of morally cool. I mean, you know, maybe you can argue it just encourages reliance on fossil fuels, and you're gonna just be like, well, we've solved the problem. No, now they're just gonna produce more carbon dioxide gas. But still, as a carbon capture idea, I still think it's pretty cool. If you can directly capture it from the air, that's even better. That would be a holy grail of MOF chemistry.
as I've only met one of them, Omar Yagi. We were at a conference together quite a small conference with several Nobel Prize winners and several more people who might win Nobel Prizes. And in the group photo, you can see I'm just standing behind Omar Yaghi.
There they are, Gary. There they are.
Probably the closest I'll ever get to a Nobel Prize winner.
It tells you what this one is. You haven't even.
All right. I did not expect to be able to drag this reaction out to about 40 minutes, but hey, I'm happy with it. And hopefully you were too. Hopefully you learned something about the Nobel Prize in Chemistry this year and how, like, there is a relatively new thing that might make it around the corner and start popping off to, like, you know, applications everywhere. Now we'll get to our main event, a 60-minute video on NileRed making liquid nitrogen from scratch. We'll do so though after a quick break because I need to go and pee as usual. So give me just a moment. I will be right back and then we can get back into it. Alright, welcome everybody. Scorebar, you definitely were here, and you're a nerd for it. You can't hide from me. And Proto, hello. Nice listening to Icebrain during your morning commute today. Ain't that funny? Love how things wrap around like that. It's one of my standard items in the playlist here. I love Icebrain. I haven't played 02 in a long time, but this is one of the better tracks from the Zero series, in my opinion. Alright. We can move on to our main attraction here soon. First, I'd like to explain the concept that we're going to be working with. God, hold on. Can I would love to blow this up and make this like the big screen, but I don't feel like messing with that live and causing a disaster and it not actually capturing correctly. Yeah, okay, so we're going to be going on to NileRed's video on making a lot of liquid nitrogen from scratch. And I'm curious to see what this is going to be like, because there is a pretty... I don't know if he's going to do this the normal way or not. Knowing him, probably not. But liquid nitrogen is a fairly inexpensive commercial product, at least as far as, you know, specialty chemicals go, because it's everywhere in the air. The air is like 70% nitrogen, actually. And so, if you could just take that, cool it down a lot, then you can get liquid nitrogen. The question is, how do you cool it down a lot? Well, and this is something that I'm going to try my best to explain, although it has been a very, very long time since I've had to actually apply this to my chemistry or my life. So I'm probably going to get a couple things wrong, but the Joule-Thomson effect is how we typically would manufacture cryogenic liquids. So the Joule-Thomson effect describes the phenomenon of if you have a bunch of gas particles... maybe I could have given myself more space for this. Uh-oh. Everything's lagging again. Why? Why you lag? Maybe because there's like video action going on the other screen. It's getting confused. If you have a bunch of particles like this, maybe turn the music down a little bit further too. Okay, and disable the OBS preview. Save a couple of resources. Okay. If you have a highly compressed gas in one area, and you, through a semi-permeable membrane, if you can push that gas out of the confined area through a semi-permeable membrane out into the atmosphere, or, you know, wherever you're trying to collect something, the gas, most gases, will actually cool down going through that kind of small space and expanding out into the atmosphere. In fact, that cooling is usually so dramatic that you can get things that are you can take gases that are at conventional temperatures, from either room temperature to more like a simple refrigeration kind of temperature, and bring that temperature far, far below where it started from. So you can go from something, let's just say that this is, we'll assume that what's inside of the container I've drawn here is like, I don't know, 200 Kelvin? Actually, that's probably still too low, because then that would be room temperature 0. Let's just go with room temperature, just to make things easier. 273 Kelvin. And then after this process, you actually get something down to 70, like, how about 50 Kelvin? That would be a liquid nitrogen temperature. So you get this dramatic cooling process that occurs by ejecting it out of the pinhole. And this is where I'm going to get the math maybe a little bit wrong. This happens for most gases because as you apply work from, like, say, a piston over on this side here, to compress it out of the pinhole. As you apply work into those gas molecules, you are putting in energy that you need to put in order to separate the molecules from each other. And as a result, the internal energy of the collection of molecules goes up because you had to put work into it to kind of compress it and push it through. And so if the internal energy of that goes up, no, the potential energy of it goes up, that's what it is, then conversely, the kinetic energy of the atoms goes down. This is a heady concept that, again, I have not taken thermodynamics in like maybe 4 years. Actually, no, it's been like 7 years, 8 years. I did have like the Wikipedia up a while ago, and the equation that describes this is H is equal to U plus PV. P represents pressure, V represents volume, and this is meant to be meant to be applied as a change in enthalpy is going to equal your, well, H is enthalpy. Change in enthalpy is going to equal a change in your internal energy U minus the change in, not pressure, and change in volume, not, okay, hold on, let me re-say that. Your change in enthalpy is going to equal your change in internal energy plus your change in pressure and volume, pressure times volume, not the change in pressure times the change in volume, being two very different things. This would be the change of PV, not the change of P times the change of V. And what I kind of tried to describe there is that this is a constant enthalpy process, which I can't take the time to get into all of that, so you kind of have to just take my word on it here. But since that has to be constant, then any change in PV has to be represented by a change in U, and they have to be proportional to one another. U breaks up into potential energy. Let me just actually write that instead. Or type it instead. So, potential energy it becomes a change of potential energy as well as kinetic energy. Gotta get the pen back. There we go. And so if again, this is starting to dig into the recesses of my brain. And kinetic energy, well, this one's easy enough, can be expressed for a gas roughly at, well, for anything, as 1/2 times mass times velocity squared. And so the relationship between temperature and kinetic energy is that if you have less velocity, or I'm sorry, which is kinetic energy of a gas and its temperature are proportional. So if you lower the velocity, average velocity of the molecules, you're going to lower the kinetic energy, which means you're going to lower the temperature. And so if the temperature ends up lowering, then your change in PV, the math gets complicated again. But if your kinetic energy and your potential energy need to add to a value that is equal to the negative of your change in PV, then in order to balance this equation out. So if your PV ends up, if your delta PV ends up being positive, then potential plus kinetic needs to be negative, and that it results in, like, your temperature dropping to again. If I had more time to prepare for this stream, I would have completely refreshed myself. I found kind of an overview, and this can maybe express it a little bit better in terms of like intermolecular forces, which is the better kind of way to think about it, but it's harder to express in math. So, under the Joule-Thomson effect, a gas will cool or heat up as it expands or compresses, if the conditions are right. This change is not due to the work done on the gas or by the gas, since it occurs in an insulated system, but is instead a result of the intermolecular forces present in the gas. When a real gas is compressed, molecules are forced closer together, leading to an increase in intermolecular attractions. This process releases heat, causing the gas to warm up. So that's just when you're compressing something normally. Conversely, when a gas expands, the molecules move apart, and the intermolecular forces do less work, absorbing heat and thus cooling the gas. The Joule-Thomson coefficient is a key factor in whether a gas will cool or heat up. The coefficient is defined as the change in temperature divided by the change in pressure during a throttling throttling process at constant enthalpy. The coefficient can be positive or negative, depending on the types of gas and initial conditions. For most gases at room temperature and moderate pressures, the coefficient is positive, meaning the gas cools upon expansion. The inversion temperature is the point at which the coefficient changes sign, and above the temperature, the gas heats up during expansion. Again, it's heady concept. We didn't even need to know this to get in the video, but this is how, like, liquid nitrogen is typically made, with this Joule-Thomson effect, squeezing it out of a small membrane, expanding it, temperature goes down, and has to do with the intermolecular forces not being bonded as much, dragging into each other as much, and so they do less work on something, and you get more heat absorbed, and I paid only so much attention to thermo because I knew that I was not going to need it for like most of my chemistry career. Apologies to any thermochemists out there, or physical chemists out there, but this is physics. This is not chemistry. But yeah, so I'm curious to see how NileRed's going to make a shitload of liquid nitrogen, and if he's just going to use this effect at a mass scale. Maybe he'll explain it better than I do. I hope that he does. So let's get into it.
Brilliant. As far as I can remember, I've always been kind of fascinated by liquid nitrogen, which is just this weird, foggy liquid that's so cold that it can freeze things to the point that they can shatter. For whatever reason, I've also always wanted to be able to make it myself, just like how I'd seen it done on channels like Applied Science and Veritasium. And in early 2020, I actually ended up reaching out to Veritasium and buying the cryocooler that he used in his video. I also eventually got it going, where the first thing that I did was make some liquid air, which was technically about 80% nitrogen and nearly just as cold as pure liquid nitrogen, and at the time, I felt that this was good enough. However, in 2023,
However,
as I
it's
started
not pure
working
liquid
on more
nitrogen.
and more projects that were going to require liquid nitrogen, like the entire air series that I'm planning, where I turn air into things like alcohol, gasoline, and even a bomb, I started thinking about making it again. More specifically, I started thinking that it would be really cool if I could only use my own homemade liquid nitrogen for all of these projects, and for all of my future projects in general, and I ended up getting really fixated on this idea.
He really wants
The only tricky
Big
part,
Boom.
though, was that for this idea to work, I would need to be able to quickly produce a lot of liquid nitrogen, which, unfortunately, wouldn't be possible with that cryocooler that I had bought years ago.
It's too
It
tiny.
also turned out that any commercially available system that was able
It's
to
gonna
do
cost
this
him hundreds
was
of thousands of
shockingly
dollars.
expensive, where even on Alibaba, the lowest price that I was able to get for a cheap Chinese system was for $24,000, which was way more than I was ever willing to pay.
That is reasonable for the budget of a chemistry department. That is not reasonable for the budget of a guy making YouTube videos.
Instead of just immediately giving up on this idea, though, I started thinking that it had to be possible to build one for cheaper. At the same time, I also slowly convinced myself that this was something that I would actually be able to do, despite having basically no experience. And well, long story short, I decided to just go for it. So I
decided just go for it. The NileRed story.
And the first thing that I did was search the internet for anything that I could find about making a massive liquid nitrogen generator. And unfortunately, I wasn't able to find anything.
Shocker.
However, I was able to find several really useful videos of it.
It's actually a little bit surprising. The Science Madness forums are a repository for lots of amateur chemists who like just making stuff that they probably shouldn't at home, and even, you know, have DIY guides on how to make a fume hood at home, or how to make electrochemical cells at home for nasty electrochemistry, or, you know, all sorts of dangerous shit that you really shouldn't do yourself, but because, you know, science demands that you make sodium in your home, people have found out. And it's kind of surprising that there isn't even at least one hit on Science Madness on how to make a whole bunch of your own liquid nitrogen in a large scale. Maybe there's at least some scale, but, you know.
Being done on a smaller scale, where besides the ones that I mentioned earlier by Applied Science and Veritasium, some notable examples were this one by Ben and Builds, this one by the King of Random, and this one by I'm Smoother. As an honorable mention,
that's still expensive
I also want
looking.
to point out this one by Hyperspace Pirate, which I didn't see at the time because it was posted shortly after I started this project, but I think it's really impressive, especially because it was done entirely from scratch using a bunch of old AC parts.
Oh my god, I love how the main chamber up here is also like made out of tinfoil too.
With that being said, though, after seeing all of this, and after examining every commercially available liquid nitrogen making system that I could find, I was able to get a rough idea of what I had to do. I was also able to put together a rough...
Which, I could also say, this is like doubly bad as an idea to try to do it yourself as a chemist, because of like, not only were you attempting to get something extremely cold that could easily like make your fingers so brittle they'll snap off and give you cold burns like very quickly, you're also working with big changes in pressure, so risks of explosions and implosions, and like just trusting that your equipment that is not rated for this whatsoever is going to hold. Like it is a capital B bad idea to be doing this.
Plan of what I would need to build.
But he's a professional with a giant budget, so.
Where the first major component was going to be something called a membrane nitrogen generator that would allow me to generate pure nitrogen gas from air. The second would then be a massive cryocooler that I could then use to liquefy this nitrogen gas.
What the hell is the shape of that thing?
And the third would be a really big insulated dewar where I could then collect this liquid and ideally hold up to 100 liters of it. Along with all of this, there would also, of course, be a bunch of wires, hoses, and miscellaneous parts and accessories to make it all run, but at least for now, I felt that the best idea was to just focus on these three main components. And by
everything else can be
focus,
picked up the
I
hardware
mean that
store.
I had to somehow obtain them, which I knew was going to be both difficult and potentially super expensive. What did make things a lot easier, though, was that I actually already had a membrane nitrogen generator that I'd gotten from Veritasium when I bought his cryocooler.
I remember watching this video. This was cool because Veritasium was like one of the first people to like really, I won't say the first people to do this on the internet and show how to do it, but maybe one of the first people to show it with a large audience and a kind of professional build, all things considered, rather than being, you know, just shit that you found in the in the back of the scrapyard. I remember this video. I remember it fondly when I used to watch Veritasium.
The only tricky part was that I'd never tested it myself, and I wasn't entirely certain that it still worked, but it seemed perfect for what I wanted to do. It was also extremely convenient that I already had it, especially because even used, these things were apparently going for thousands of dollars. With that being said, though, this then...
Which, yeah, I mean, I can't blame it for being that much more expensive. Those things basically work by just being size filters. Like, just just to kind of maybe describe it a little more, like the whole like I'm gonna try and draw these to scale in some kind of sense. So let's see, you could have a nitrogen molecule here, roughly equal size there. You then have oxygen this size, and you could also say have carbon dioxide. That looks here. Let me just. That makes it look a little better rather than having a pair of yiddies on screen. Let's see. Bond that to a carbon in the middle. Like, you basically have to filter by size the fact that nitrogen is slightly smaller than, like, all of the other components of air that are major in any way. And, like, that would be very expensive. It's essentially literally just weaving something that, like, has gaps that are, like, this big, but gaps that are, like, too small for oxygen and carbon dioxide to fit through. Like, that is a very impressive feat of I mean, it's not being literally woven, but it's a pretty impressive feat of engineering to actually be able to get something that's like that small to be able to have only nitrogen pass through and filter out argon, oxygen, carbon dioxide, water too. Water's a big one to have to filter through. So like water would probably be smaller in some senses compared to nitrogen, but being a triatomic molecule, being a triatomic molecule, you end up just having like some hydrogens here. Still can't quite fit through. It's very difficult to do. There might even be like desiccant in there to kind of prevent the water from going through. I don't quite know exactly how every bit of it works, but it's largely just filtering. And to have something that literally only nitrogen, dinitrogen, can actually get through, it's not easy. So of course it's going to cost thousands of dollars for a glorified tube.
Meant that I really only had to get my hands on a massive cryocooler and a huge doer, where at first, I was actually tempted to try and build them myself. However, after thinking about this for a long time, I realized that this was a completely unrealistic idea, and if I wanted this project to even have a chance of succeeding, I was gonna have to buy these parts pre-built. I also decided to just keep searching online every day, where I was hoping that I would eventually find the parts that I needed.
Some guy on
and that they
Craigslist just
wouldn't
selling
be
an
too
industrial
expensive.
liquid nitrogen doer.
It was then one painful month later when I stumbled onto this cryocooler, which was normally meant to be used in an MRI machine, and I felt that it was my best option. This was because, as far as I could tell, it was one of the most powerful cryocoolers that I could reasonably get, and it was at least several times more powerful than the little one I got from Veritasium. As an added bonus, it was also theoretically capable of getting cold enough to make liquid helium, which is way colder than liquid nitrogen, and I started getting excited about the idea of using it for a future liquid helium project.
Yeah, liquid helium is also a really cool, like literally a really cool liquid. That negative 269 Celsius, that's, if memory serves, that is 4 Kelvin. That is 4 degrees above absolute zero. Helium is one of the lowest liquefying compounds in existence, and I believe no, you can you can make solid helium. It's just that that's the point where you start getting like 0.0001 Kelvin or something. It is very, very, very cold. It's very hard to come by, and it has liquid helium only has a few applications, but they are ones that are critical to science, like keeping magnets in NMR or MRI machines extremely cold, so that way they can function very well. And you have to use that as like the inner layer to like keep things really cold and keep the magnets shielded and protected and operating at the correct temperatures. But then to kind of help shield the extremely cold liquid helium from evaporating, you have to shield that in liquid nitrogen, which is still warmer, but is at least not room temperature. It is still, negative. There's only 77 Kelvin rather than, 273. And you have to keep refilling it, and it's liquid helium is very expensive, and also hard to come by. And there is extensive recycling systems within any building that uses it, because getting new liquid helium is very, very expensive and a pain in the ass to try and recapture.
There was one major downside, though, which was that it wasn't exactly cheap, and it was about $5,600. However, from what I could tell...
Hi, Bear. Mega Man 02 is dumb after all. Look, when I first played the game, I agree with you. Going back to play it again, it's not that bad. I have to give it another shot to actually fully play the whole thing again, but, after you get used to the whole Zero series, everything kind of starts to click into place. You have a Danny DeVito, oh, I get it now kind of moment. But welcome. We're talking about making liquid nitrogen at home in NileRed's crazy setup, where he's purchasing now a cryo cooler that's normally used an MRI instrument to actually get nitrogen very cold. I talked about some science about how he might be doing it with the Joule-Thomson effect, but he's maybe not got there yet. We'll see.
A really good price, because unlike every other one that I found, which was around the same price and heavily used or in unknown condition, this one was supposed to be brand new. In my opinion, this meant that there was a much higher chance
check
that
Mega Man
it would
Zero
work,
next time you play
and that
it.
I was way less likely
Would have liked
to be
come
left
tonight,
with
but,
a giant and expensive piece of crap that may or may not be possible to repair.
Oh, NileRed.
So
That's
I
never
just
stopped
went
you
ahead and
before.
bought it, and only a few days later, I received this really big and heavy box.
Not at all sketchy
I then
looking
started
package.
opening it, and up until now, part of me was honestly a bit worried that this deal was too good to be true, and that I might have gotten scammed, especially because the seller had just joined eBay and had zero feedback, except that thankfully wasn't the case. This was because inside of it, there was in fact a cryo cooler, and at this moment, I was both relieved and pretty excited.
Okay, my question is, though, if you picked this up from eBay, where was this scavenged? Where did the seller scavenge this from? Because there's no way that this was just some guy who actually works at a plant that makes these cryo coolers just went and took one home and sold it on eBay. That doesn't make any sense. This had to be somebody who explicitly scavenged this from, like, an MRI that was being decommissioned, or... I mean, it had to be. There's no other way to do it. Like, you're not going to find one of these intact in a scrapyard. Like, you had to have scavenged this from a university or a hospital that was taking their MRI down. And instead of just letting it go into the refuse/recycling stream, like the facilities manager probably would have wanted to do, just fuck it. Take it home, sell it on eBay. Someone wants it, right? Surely somebody wants it. Trash dumps. Yeah, if only.
Yes. It's real. I was not scammed. Or, I hope.
Yeah, no, it doesn't work.
It works,
haven't tested it yet, Nigel.
It does look
Nigel.
good, and it's also very heavy.
But anyway, with this hopefully functional cryo cooler in hand, I was officially $5,600 deep into this potential disaster of a project.
You've been
and
worse.
What I had to do next.
He's been like
was
25K
sink
deep
even
in the
more
project
money into
sometimes.
it. So I just hopped back onto eBay, where my goal now was to get the last major piece, which was the large doer. And while looking for the cryo cooler, I had actually found this one. That seemed pretty ideal. This was because, just like the cryo cooler, it was apparently brand new.
Again,
and
where is the scavenge from?
Reasonable price of only around $1,100, which was extremely cheap for a doer this big. As an added bonus, it was also technically made for liquid helium, meaning that
It's
it was
actually
much
rated
better
for this.
insulated than a typical liquid nitrogen dewar, and at least in theory, it would pair super well with the cryocooler and potentially allow me to make liquid helium in the future. The only downside with this dewar was that it was apparently 30 years old, which really made me worry that it might have some major issues.
Honestly, though, it's probably better than a lot of universities. There are many chemistry buildings and universities that are, say, from the 70s, and, you know, optimistically, maybe they replace their infrastructure every couple of decades, but realistically, no, there's like 60-year-old equipment still being used there. So to have something from the 90s be a liquid nitrogen dewar container, you know, that's not terrible. Also, like, you're, you know, on a home scale, this isn't like industrial, you know, manufacturing. You're never going to have all that much in there. It'll be fine.
And the seller provided no guarantees that it would actually work. This meant that
So they
just
found it
like
in the
the
back of a
cryocooler,
warehouse then for
there
it to
was
be
a
new
decent
and 30
chance
years old?
that it was just a complete piece of trash
Nearly
that could end
35.
up being a total waste of money. However, at the same time, it was only $1,100, which was way cheaper than anything else that I had found, and I decided to just go for it.
So it's time to gamble.
It was then a few weeks later when I received this extremely large wooden box, which I quickly cracked open to reveal my beautiful duo. After that, I very carefully started taking apart the crate with the help of my favorite hammer, and once most of it was gone, I was able to use some 2x4s to very expertly unload it.
You know,
I should also say that this probably...
Nigel, you do have other people in your office. You are not a sole employee of this lab. You have other people you could have had help you move this, or maybe get some equipment to move it. You didn't have to fucking risk crushing yourself.
It wasn't the best way to unload it, but I felt that it was fine, and I did put a lot of effort into making sure that the dewar wasn't damaged.
Yeah, the safety precaution
point,
of I thought it was
the
okay.
Dewar, cryocooler, and nitrogen membrane generator secured, I now had the 3 major components of the setup, which I thought was pretty exciting. The only unfortunate part was that I actually wasn't quite done buying equipment, and I still had one last but extremely important thing to get.
Yes, the
which was
compressor.
a compressor to run the cryocooler. This was
Can't exactly get things cold without some kind of compression cycle.
also something that I had no idea that I needed when I first started this project, and this was mostly because I didn't need one for the cryocooler that I got from Veritasium, and it also didn't seem to be needed in the applied science video. It turned out, though, that for those smaller cryocoolers, the compressor was just integrated, and for a massive one, like the one that I had just bought, I was going to need a dedicated external one, which, as far as I could tell, wasn't going to be cheap. In fact, it was looking like it was going to be by far the most expensive part of the setup, and after searching for a really long time,
Come on, Nigel, make one yourself.
I ended up coming across was for just over $10,000. In my opinion, this price was honestly kind of shocking, but at the same time, it was actually cheaper than pretty much everything else that I was able to find, and as far as I could tell, it seemed to be a pretty good price. Most importantly, though, it seemed to be in really good condition, and it claimed that it was taken from a working environment, so at least in theory, it shouldn't have had any major problems.
Okay, so if he's purchasing this, then he's like, what, roughly 18K in the hole? He probably could have, well, okay, no, the cheapest thing he showed at the beginning of the video was like $130,000, so maybe he's still technically getting a net benefit of constructing his own liquid nitrogen compression rather than just, you know, purchasing a commercial one.
However, just
still
like
ludicrously
everything else,
expensive.
there was, of course, no guarantee, and at this point, I was genuinely thinking about just bailing from this project. This was because it was a lot of money to spend on something that might not even work,
Come on, Nigel, some cost fallacy.
Other money that I had already spent, this would now put the project at nearly $17,000, which was way more than I ever expected to pay. At the same time, though, this was technically still over $7,000 less than the cheapest Chinese system that I was able to find, and moreover,
only
I just
7,000?
hated the idea of quitting after already spending
So that's actually not that
dollars
much money
and then
saved.
being stuck with a useless cryo cooler and a giant doer. So I decided to take a few days to think about what to do, where I knew pretty much the whole time that the smart decision
someone else on
was
eBay
to
scooped you
probably
up.
just cut my losses. Except, long story short, I decided to just go for it. I then anxiously waited, and a couple of weeks later, this tiny little pallet arrived, and after slicing open all of the plastic and the packing stuff, I revealed the worst financial decision that I had ever made.
See, NileRed, that's the thing that separates you from a lot of other YouTubers, and especially chemistry YouTubers. Not only do you have the potential budget to do extremely expensive, crazy things like this, you also just have the emotional wherewithal to just say, screw it, I'm gonna spend $30,000 on some esoteric piece of equipment for a project and for a video. That's what separates him from all the other ChemTubers, and still makes him entertaining to watch as a result.
In fact, unlike with the doer and the cryo cooler, it was actually hard to feel excited at this moment, and
it's like what makes him successful in the first place.
I think what I felt was mostly regret. But with that being said, at this point, I now actually had all of the major components that I needed to make a huge liquid nitrogen generator, and with all of this, the first thing that I did was absolutely nothing.
Hooray!
This was
Typical
because every time
NileRed,
that I
like,
even thought of starting this project,
1 year
I was
hiatus.
almost immediately overwhelmed with anxiety, mostly because I had basically no experience with any of this, but also because I was really afraid of finding out that I had just wasted a ridiculous amount of money on a bunch of non-functional crap. So, out of sheer avoidance, I ended up just letting it all sit around and collect dust.
I worked on
until
other projects.
One day, I randomly woke up, and I felt that I was ready to see just how badly I'd screwed up. I then just went ahead and jumped right into it, and I still wasn't entirely sure where to start, but I felt that the best first step was to figure out how to mount the cryo cooler to the doer.
Again, to be fair, this is how every single one of NileRed's projects has started, probably for like the last 3 or 4 years. He buys a bunch of expensive stuff, he sits on it because he's anxious about using it and seeing if it actually works or not, and, you know, if he can mentally prepare himself for a financial failure. And then one day he wakes up, and it starts working. I'm sure there's ones that don't start working that we never get to see or hear about, but as far as we know, they all seem to start working. And look at that. Wouldn't you know it? He picked himself up after enough days and got this one off the ground, and now we're going to watch a man make a lot of liquid nitrogen.
I also felt that the fastest way to do this was to just steal the design from someone else.
Yeah,
I spent a long time looking at the Chinese systems that I got a quote for, as well as any commercially available ones that I could get a photo or video of.
Yeah, no, I would not dump 17K into doing something experimental like this. I mean, okay, if it was literally my job to try to make content out of doing experimental stuff, I would, and that's his job, so, like, it totally makes sense for him to do it. But, like, for me, personally, trying to avoid, like, paying an extra $7,000 for some, you know, system that already is pre-set up on, a rat chewed through a wire, and everything stopped working, and no one's bothered to fix that wire quite yet. Hello, it seems that we are back. Hi, chat. I just spent a little time with the VOD watchers there. Don't worry about it. I just noticed that OBS was dying. But yeah, no, this is too expensive for me to spend my own money on. But if I actually had, you know, the budget that NileRed does and did this for a living, then, you know, makes more sense.
Then, when I eventually felt that I had a decent understanding of what I had to do, I took a bunch of measurements on the top of the doer and around the cryocooler mounting ring, and I reached out to my friend Tommy to make a 3D model.
I will say, it's fairly impressive that NileRed could basically glean a liquid nitrogen condensation schematic just by watching a shitload of YouTube videos. That's like that. I mean, unless those YouTube videos gave measurements, which I don't think they did, considering he's used the word steel. Yeah, that's pretty impressive. Also, hello Tommy, and also in the background, hello Styropyro. I'll be reacting to you and your fanciful physics experiments one day. Yeah, it is. It's definitely a gamble. It's not. There's a lot less to gamble on if you make content out of streaming games, for example. But high risk, high reward, right? And he's managed to craft a very good ratio of risk to reward.
He then
Whole
quickly
career.
sent me back this, which I felt looked pretty good.
A 3D
and
model.
My basic idea was to get this made out of a giant slab of stainless steel and to mount it to the top of the doer. With this in place, I figured that I could then attach the cryocooler through the giant hole in the middle, and in the other holes, I would then hopefully be able to add some very important things, like my nitrogen gas input, as well as a pressure gauge, and some safety valves. In my mind, this seemed like a decent design, and after a
the
few
fourth mystery hole
alterations, and 3D printing it a few times to make sure that it fit the cryocooler, and that it lined up with all the holes in the doer, I had Tommy send it over to his friend to make it out of stainless steel. I then patiently waited, and
God, what connections does Tommy have that just have custom stainless steel parts made?
Eventually, I received this nice little package from Husky Machining, and I quickly opened it up.
No, it's made by a furry company.
Beautiful plate.
Oh well,
That's nice.
They do good work.
The moment that I saw it, I was also both really impressed with how it turned out and excited that it finally seemed like this project was starting to move.
It's ridge textured like that.
That wasn't until I suddenly realized that I had accidentally screwed up the 3D model, where not only did I make all of the holes around the center way too big and not get them threaded, I also somehow didn't ask for nearly enough. So, unfortunately, I was going to have to fix this.
Well,
and
now
I
you have a
ended up
nice
spending
frisbee.
the rest of the day drilling all of the extra holes, then tapping them to thread them, and adding inserts to make them the proper size.
Wow.
What also made things extra painful.
Again, it's a good thing that NileRed is, and I mean this in the literal sense, he's less of a chemist and more of an engineer. His background is in engineering, because this is the point where a chemist, like, our loved Tom Explosions in Fire, would probably just throw his hands up and say, well, fuck it, I'm just gonna order another stainless steel ring with the things corrected this time. Having engineering knowledge and actually knowing how to work with your hands kind of helps sometimes, and you just need to be able to say, like, okay, well, didn't have enough thread screws, I guess I'll just go ahead and, or thread holes, I guess I'll just go ahead and, model the stainless steel to my what I need. The stainless steel is my canvas, and the drill bit is my brush.
Was that I tried to speed things up by using a drill to thread the holes, which was a terrible idea. And I ended up spending hours.
The brush is not very strong.
The broken tap.
It was perhaps purchased from the dollar store.
When I was eventually done with that, I was very happy with how the plate was looking, and what I had to do next, which will make a lot more sense in a minute, was build a small metal frame. This was also something that I thought would be really fast, except it ended up taking me almost an entire day, mostly because I'm kind of terrible at welding.
My eyes.
When I was eventually done, though, what I ended up with was surprisingly nice.
Hell yeah.
Considering the disaster that went into
it's
making
like
it.
Half a table right there.
I was pretty happy with how it turned out. But moving on, with my hopefully sturdy frame now built, I quickly dropped on my big steel plate, and I added 4 bolts to loosely hold it in place. Then after that, I added a mounting ring that came with the cryocooler, where I was very happy to see that all of the extra holes that
came with it
actually lined up perfectly.
Wow, look at
that. And after tightening down all of the screws, I went and got my expensive and heavy cryocooler. I then very carefully lowered it in, and it was really satisfying when it seemed to fit perfectly.
How about that
It was also
shit?
really nice
Because
to
I could
finally
never
have
do
it out of the
this.
box and sitting vertically like this. And at this point, I should probably say that the main purpose of this whole frame setup was to basically just be able to easily test out the cryocooler without having to involve that potentially broken doer. The only unfortunate part with all of this, though, was that before I could even think about testing it out, I was first going to have to get that really expensive compressor going, where I was genuinely super afraid that it was going to be totally non-functional, and that it was going to completely ruin this entire project.
Well, I mean, you know.
However,
Thankfully, it seems like it works, but, you know, honestly, at this point, if you have sunk this much cost into your project, you might as well just try to buy another one to make the project come out the other end if this one doesn't work. Like, I don't know. The sunk cost fallacy is called the fallacy for the reason, but, you know, again, I'm willing to take at least another gamble. There's a statistically probably a good chance that one more gamble will yield you net profit from the ad revenue and sponsor money on this video. So, why not?
long story short, it only ended up being kind of non-functional. Where to
Ah,
get it
kind of
going, I
non-functional.
did have to do a few things, like swap out this weird power socket on the front for a proper power cable, and repressurize the system to 200 psi using high-purity helium gas
That's probably
by
expensive.
following a kind of long and painful procedure that I had found in its service manual. At the same time, I also ended up having to replace the crusty water fittings at the bottom so that I could attach this massive water chiller to cool the
Oh my
compressor.
god, that is
And I had to
huge.
bring in this 480 volt 3-phase transformer to power the compressor, where both of these were originally meant for one of my air projects, and I had actually gotten the chiller for free.
Again, shit that nobody casually has lying around except this guy because he's already in the business of making huge at huge scale esoteric chemistry engineering projects. This probably would have been like another several $1,000s in the hole if he hadn't already had it for, you know, another reason. It's like how if you know, have spices in your spice cabinet, you're not it might cost a lot to buy a bunch of different spices up front to make like your favorite like butter chicken dish, but then you're going to have all these spices in your cabinet now for the future and it's not going to incur costs. Just scale that up by several, like maybe a factor of 100 or 200, and it's basically the same concept.
When I was eventually done all of that, though, I had what appeared to be a fully functional compressor, which was really relieving to say the least, and now I was finally able to get back to testing the cryocooler. And by that, I mean that it was finally time to see if it would actually work, or if it was in fact a giant piece of crap that may or may not even be fixable.
Which, oh yeah, finally, we're actually getting to the thing that like I drew on screen again, where it's like, again, because I poorly explained this the first time and probably won't be able to explain it again right, but cryocooler or compressing nitrogen or air in this case just down to liquid air involves pushing through air at a pressurized and room temperature, a pressurized small vessel at room temperature through a small semi-permeable membrane, pushing that out into, in this case, it's just going to be the atmosphere at the bottom of that cryocooler adapter thing. That's going to cause the temperature to drop because energy is being put in to separate the atom or the molecules, and you need to, it's a constant enthalpy process, and so that is needed to counteract the loss in kinetic energy. The thermodynamics was 8 years ago. I'm not going to try to explain it again, but you know, the phenomenon is you're going to expand the gas and it's going to cool down.
But with that being said, there was only one way to find out, so I just immediately got started, where the first thing that I did was connect a power cable. Then after that, I quickly added some gas fittings that I bought from the company that made the compressor, along with a helium line, and this was because the first thing that I was going to have to check was whether or not there was still any pressure in the cryocooler. Where if there wasn't, then, well, At least according to the company that made it, this would likely mean that it had been infiltrated by air and moisture, and that it probably wouldn't work. And I was honestly expecting the worst. However, I almost immediately
Pressure
heard a
escaping.
hissing sound when I opened the valve, telling me that even after 7 years, it was still under pressure, and that somehow I had apparently gotten super lucky.
That's good.
With that confirmed, though, I then quickly refreshed the helium in it by following a procedure that was very similar to the one that I used for the compressor, and when I was eventually
Another large
done,
pain in the ass.
I quickly got rid of the special fittings. I then went and got some really long and big helium lines, which I was gonna use to properly connect the compressor to the cryocooler, and I bought them from the company that made the compressor. What was also very important about these helium lines was that they were pre-charged with 200 psi of helium gas, which matched the pressure of the compressor and the cryocooler. This way, when they were attached, they wouldn't introduce any air or moisture, which would contaminate the system and ruin all of the cleanup work that I just did.
Oh, huh. Okay. I thought that these were just kind of empty tubes and, like, you know, kind of connect through either end. They're just designed for work with liquid helium or cold helium. No, apparently there's just like a special flanges at the end where it's like the inside of the tube is already charged with helium, full of helium, and the only little bits of air and moisture getting introduced are like at the actual fitting heads themselves, and those seem to get kind of, you know, displaced when screwing things in. And only once you actually screw them in does like the special engineering kind of take its place and push a ball out of the way, so that way it then actually connects into the rest of the tubing. Huh, fascinating.
But either way, with all of this in place, in theory, the system was now ready to go, and to see if the cryocooler would actually work, all I had to do was turn on the compressor. So that was exactly what I did by just clicking the on button, and almost immediately, I was greeted with an interesting sound.
Okay.
This was also exactly what I was hoping for, because it was very similar to the cryocooler sound that I heard in the background of some videos about MRI machines, and this was a very good sign that it was working properly.
It's also a noise that I'm very familiar with, because it's also the sound you're going to hear constantly in an NMR analysis room, nuclear magnetic resonance, which is basically it's basically MRI applied in a different way to be able to suss out the structure of molecules. And yeah, if you step foot into your chemistry department's NMR facility, you're going to be hearing like 7 of those things pumping on and off, and it's going to sound like there's birds chirping in the area because of how high frequency it is. It's a very nostalgic sound that any chemists will both associate the sound with crippling failure as they realize the sample they've put in is just a mix of brown tarry mush and has no product of what they want in there, or overwhelming joy as the product they've spent months trying to make actually comes out super pure in the spectrum they actually take of the compound. Man, that sound makes you feel some kind of way, and either kind of way it makes you feel, it's gonna be an extreme feel.
So far, though, it still seemed to be around room temperature, and to know whether or not it would actually get cold, I was just gonna have to wait. So I just sat there and I patiently stared at it.
Like watching paint dry.
Over the next 20 minutes, I could faintly see it turning white because frost was forming, which confirmed to me that it was definitely getting cold. This was then further confirmed when I tried touching it, and just by the sheer pain, I knew that it was down to at least -80°C or -112 Fahrenheit. However,
I'll also say I love that still this late into his stream, to his video making career, NileRed does not ever find it necessary to like get a camera close to make a close-up shot of these kinds of things when he notices it working. He just says, I'll just zoom in post later. It's gonna be grainy, but like, yeah, it's fine. It's fine. I guess maybe he's not thinking about it when he's actually doing the work. Usually people come up with the ideas after they're done recording and making the video and making the narrative afterwards, but still, it's just funny. Yeah, screams ow, touches it again. You gotta, that's, it's science, it's reproducibility. You can't just accept that the one time you touch the cold stove or the cold cryo compressor that it's cold. You gotta do it multiple times, just like kids in ovens, It's a scientific method. It's gotta be reproducible.
This, of course, still wasn't even close to cold enough to make liquid nitrogen, and to help it out, I decided to insulate it a bit by adding a small dewar over the second stage of the cryo cooler. This part was also, in theory, the part that got the coldest, where it should have had no problem getting all the way down to near absolute zero, and I was really curious to see what would happen. More specifically, I really wanted to see if it could start liquefying the air around it, because if it could, this would prove that it was capable of making liquid nitrogen, which forms at around the same temperature.
Okay, actually, hearing how he's describing this more, it might not be the Joule-Thomson effect. Well, at least it might not be directly expanding the nitrogen out of the end of the probe here to try to make liquid nitrogen. It's more actually that this Joule-Thomson effect is happening within that pump to cycle heat in and out in the correct ways. Cycling that heat, cycling the coldness on the other side of this presumably copper nodule at the bottom here, making that cold enough in order for liquid air to condense on it, which I'm guessing he's going to have to do some extra finagling to make sure that only liquid nitrogen is around this in the future for the rest of the project.
However, even after an hour, nothing was there, and I was honestly starting to get really worried.
Sag.
This was because it was very possible that the system was working well enough to get really cold and to free some moisture out of the air, but it was then failing to get cold enough to actually condense the air. Just for good measure, though, I decided to let it go for another 20 minutes, and I was honestly starting to really lose any hope, until I noticed that there was actually a bunch of liquid air already in the dewar.
Huh.
I was about to give up.
So apparently, I was just super impatient, and it just took a while for the whole system to cool down, and when I looked closer, I was able to clearly see some drops of liquid air.
I'll also say 2 extra things. One, probably would work faster if this was just insulated better. He just has this cryo cooler to the open to the entire room. If it was even like a barrel or something, it would be a smaller area and it would not, have this issue of like warm air constantly cycling past it. It would have less air to cool down. Also, too, man, having a glass jacketed dewar like this just for viewing, I imagine this thing must have been expensive, just so that way we can see the liquid air condensing at the bottom of this collection dewar cup at the bottom there. These are usually made out of like some form of metal, because it's just easy to shape it. Having the glass be like this, and also note the fact that these are vacuum jacketed, so like the space in between the 2 layers of glass you see, that's vacuum, that's empty space, so that way it's not it's very insulating. That's expensive, and to have glass stand up to that is also an expensive kind of glass.
I then let it sit like this, where I just slowly collected more and more, and in my opinion, this was extremely exciting, especially because it was doing it at a much faster rate than the small one I had gotten from Veritasium.
Exciting until he looks at his electricity
bill.
What
also made it even more amazing was that this second stage was supposed to have way less cooling power than the first stage, which meant that the true liquefying capacity of this system was probably at least several times more than what I was doing here. With that being said, though, I feel like at this point, I should probably explain a bit about how this cryo cooler was even working, and how it was getting so cold.
Can't let me do all the work,
I should also
Nile.
say that I think the general idea is relatively simple, where this cryo cooler setup was basically just a little refrigerator or heat pump system that exploits the fact that gas gets hot when it's compressed and cold when it expands. Where in this case, the compressor over here was compressing the helium gas that I filled it with, which was causing its pressure to spike by about 100 psi, and for it to get really hot. However, it doesn't stay hot for very long because there's a cooling system in the compressor that allows this heat to be dumped into water and pulled away by the chiller. This is also very important because this then allows the system to push cooled but high-pressure helium through this gas line and into the cryocooler, where it's able to expand. This expansion then, in turn, causes the helium to get really cold, where it's able to quickly pull a bunch of heat from the cryocooler
Joule Thompson effect.
before getting pushed out into the return line.
I know something about what's going on.
As a hot, lower pressure gas back to the compressor, where it gets compressed again, and the cycle is repeated over and over, where every time, the cryocooler gets slightly colder and colder. In this case, though, I only needed it to get down to at least liquid nitrogen temperatures, but as I mentioned before, it's supposed to be able to get all the way down to near absolute zero, which I think is kind of insane. Also, I should say that this specific cryocooler that I'm using is a Gifford McMahon, or GM for short, and it's just one of the few common types of cryocoolers out there where they all kind of work in a somewhat similar way. But anyway, after collecting...
I have no idea why the Gifford McMahon thing was important to point out. Maybe that's an engineering thing of, like, a specific type of refrigeration cycle, because that name does not ring a bell at all to me as a chemist. It has nothing to do with chemistry or, like, a chemistry cycle or anything like that. And I don't think it's a brand name, given that we've seen the branding of these pieces of equipment. So,
it for about 40 minutes, I had what looked like a pretty decent amount of liquid air, and I was really happy with how things were going. I also decided to do a quick and kind of crappy experiment where I just lit a piece of steel wool on fire, and then I tried pouring my liquid air onto it. For some reason, I thought that because it was such concentrated air, it would burn a lot better, and I guess maybe it did slightly, but it wasn't nearly as interesting as I was hoping it would be.
No, Nigel, you're confusing it for liquid oxygen. Well, okay, liquid oxygen is... Don't play with liquid oxygen. It's explosive. But, I mean, yeah, sort of. You're getting an enhanced burning effect from the, like, 20-ish% air that's compressed there, but you're also getting an extreme deadening effect from the 80% nitrogen that's there. 80-ish% nitrogen that's there. That's not going to encourage combustion. It's going to discourage it.
With that being said, though, at this point, I was extremely excited because apparently
saw a difference
most of my fears were completely unfounded, where both the compressor and cryocooler seemed to work perfectly. Now, the only remaining question was whether or not the doer was actually functional, and well, long story short, as far as I could tell, it probably was.
Hooray!
This was because when I connected my vacuum pump to it, I was actually able to pull a really strong vacuum in the space between the outer wall and the inner chamber.
Oh yeah, and that's kind of like how I was explaining before with the smaller cup. Like, it's vacuum jacketed. There's just this space of, empty, there's this empty space in between the wall and the chamber where you're actually storing things. And, without anything there to conduct the heat, the heat's not going to conduct, and so the inner chamber is going to stay cooler for longer for easier. Of course, if it was a perfect vacuum, then yeah, it would never conduct, but, well, nothing is ever perfect.
More specifically, I was able to go all the way down to at least 1 × 10⁻⁵ millibar, which was pretty much exactly what I was hoping for, and I was very happy when I saw this. This was because, at this level of vacuum, there would be a very strong insulating effect around the inner chamber, which, at least in theory, would allow me to collect and hold liquid nitrogen in it without having almost any of it boil off. With that being said, though, what was more important than just pulling a vacuum was seeing if it could maintain one once I'd sealed it up and gotten rid of the pump, and well, it seemed to have no issue doing this. This told me that somehow, and by some sort of miracle, there weren't any leaks, which was honestly super surprising to me, especially considering how old this doer was.
Yeah, you know.
But either way,
they built it
with
good
the
back
doer
then.
apparently good to go, this meant that I
Welded
could
steel.
finally start putting together the whole system. So that was what I immediately started doing, where the first step was to basically dismantle everything that I had already put together and to reclaim the mounting disc. I then
What? You mean you weren't going to just drag the whole thing connected with the with the cryo compressor or what's it called? The cryo pump, along with the compressor, along with the water cooler, along with the, you know, power supply right behind it? You weren't going to try to drag all 4 of those things onto the doer at once? Come on now.
quickly got rid of that welded frame and I dragged over the doer, which actually turned out to be a huge pain because it was way heavier than I remembered it.
Get a forklift!
After a short struggle, though, it was eventually in place.
You've already spent a shitload of money. Just get a
because my
forklift.
floor is terrible and completely uneven. While I was leveling it, I also thankfully remembered that I had to clean the inside of the doer because
Ew.
it was filled with a bunch of dirt, along with a small dead lizard that had apparently made it here all the way from Florida. After carefully removing the lizard, though, and cleaning it out with a
gross.
vacuum, I
Didn't need
felt
to see
that it was
that.
looking pretty good. And what I had to do next was fully assemble the mounting plate.
Someone did say Florida.
So,
You
I
were summoned
quickly got
again.
started
Hello,
with that
Ilvo.
by first dropping on a gasket that I'd printed out of TPU using my new 3D printer that was sent to me by Prusa. Then after that, I re-added the cryo cooler
Just in
mounting
time for the
ring
good part.
along with all of its screws, and I tightened it down.
You're just in time for the good part. He made sure that his setup works, all of his equipment actually works, and he's getting actual liquid air out of his compressor system. Now he's going to actually hook it up to this 35-year-old doer and see if he can't actually store liquid nitrogen in there long term.
And I
all it
started
took was
adding
a
all of
dead
the other
lizard to
peripherals,
get us there.
where the first was some pressure relief valves. I then followed this up with an input for the nitrogen gas, along with a little pressure gauge assembly and a large tri-clamp fitting, and this will all hopefully make a lot more sense later on.
Yeah, once
With
you
the
explain it
plate
to us.
now ready, though, I then quickly brought it over to the doer.
All
and
right,
I
sounds good,
carefully
Ilvo.
Placed it on top.
So
and I
glad you
screwed it
understood
down
everything I said,
tightly to
right?
seal it.
It'll be on the test
It was
later.
also only at this moment that I realized that I completely forgot to put thread locker on all of the screws in the mounting ring, which was very important to keep everything airtight, so I had to quickly take them all out and properly seal them. With everything now securely in place, though, I then went and got the surprisingly heavy cryo cooler, which was around 50 pounds, and it was honestly a bit nerve-wracking to carry it up the ladder.
Again,
I also didn't exactly feel
Nile, you have other people around. You don't have to hold the hope the ladder stays upright yourself. You could have someone else hold it for you.
super safe or comfortable having to lean over with it so that I could carefully lower it into the plate, but thankfully, I was able to do it without any major disaster. With it loaded
Only a
on,
minor
I
disaster.
then fastened it with some screws that I actually remembered to cover with thread locker this time, and with it securely in place, I was starting to get pretty excited. This was because so far, things actually seemed to be going together as I planned, and now there were just a few final things still left to do, like adding a large sight glass to that tri-clamp fitting from before. I
Oh.
also quickly lowered in a small
Something that is completely unnecessary on a normal person's storage like this, because looking straight down into it, like, you wouldn't be able to tell how much liquid nitrogen is in there by eyeballing it. But because he needs to make videos, he needs to be able to show us what's going on inside. I appreciate that.
small strip of LED lights through a port on the cryo
Same
cooler,
thing with the
and
fucking
together,
LEDs.
These would allow me to see inside the doer while it was running, which I felt was very important.
That's actually pretty cool. That's probably something nobody's recorded on YouTube before.
Then after that, I just quickly reattached the helium lines along with the power cable, and I carefully shoved a huge siphon tube assembly down the valve.
Oh,
that
right,
was
because it's a
connected to the pressure gauge.
tall doer.
This part was also especially important because it would allow me to actually take the liquid nitrogen out of the doer. I mean, assuming that I did end up making any. Moving on though, at this point, the main part of the system was officially done, and the only thing that I still needed was a nitrogen source, where for that, I had put together this cute little setup.
Oh yeah, the return of that
It
tube.
also might look a bit complicated, but it actually wasn't too bad.
Well,
where the main
says
part
you.
of it was just my membrane nitrogen generator. This thing over here was then just an air compressor, which would be my main source of gas, and the basic idea was that it would push high pressure air into the nitrogen membrane, which was filled with a series of hollow polymer fibers. These polymer fibers were very special though, because they were selectively permeable to oxygen and water vapor, where they would allow both of these gases to pass through their walls at a much faster rate than nitrogen.
Oops.
The result of this would then be
Okay, I guess I got that wrong then. I thought that this was a selective membrane to only allow nitrogen to go through because it should be smaller than the others. Actually, wait, no. Oh, no, I got my own periodic table things wrong. Atoms get smaller as they go to the right side, upper right side of the periodic table, not the other way around. Right, so actually, no, nitrogen would be bigger than dioxygen, so it would be actually held behind, and so water and oxygen could get through while nitrogen could not. Alright, I forget how this necessarily works then exactly to have only the thing that you're filtering out be the thing that you actually get towards the end, but we'll see.
a concentrating effect where the nitrogen in the compressed air would slowly get more and more concentrated as it traveled up the tube, and the oxygen and water vapor would get rejected out of these holes at the bottom. In theory, it was also supposed to be possible to get the nitrogen concentration all the way up to nearly 100%, which was way better than the 78% that's in normal air, and in my opinion, it's really amazing that a simple looking tube can even do this. With that being said though, once the nitrogen did get to the end of the tube, it was then just fed into a regulator to knock down the pressure, followed by a gas flow meter, which would tell me how much of it was coming out. What was also kind of funny was that up until this point, I had actually never tested if the tube even worked, so I decided to quickly do that now by opening up the gas flow and by holding an oxygen meter to the end of it. I was then very happy to see that it quickly went down to a nice reading of 0, which told me that all of the oxygen was gone and that it should have been effectively 100% nitrogen. With that thankfully confirmed, I then went ahead and connected the flow meter to the nitrogen input on the setup, and at this point, it was finally ready. What I had now should have been a fully functional liquid nitrogen generator, and after spending probably way too much time, money, and effort on putting this all together,
the culmination of $20,000 and several years worth of time. Let's see if he made something better than what he could have bought on Alibaba for another couple $1,000s.
I could finally test it out, and I was feeling both excited and nervous.
Okay. Should be good.
With that being said, I then just went ahead and got started by first opening the valve on the siphon tube, followed by the nitrogen regulator.
I feel like there has to be a problem. The video's only a little under halfway over halfway over.
The goal was to completely replace all of the air that was currently in the doer. To monitor this, I also just occasionally checked the output with the oxygen meter, and when it eventually started reading 0%, I closed the siphon tube valve, but I left the nitrogen gas input open. This then caused the pressure in the dewar to slowly rise, where I let it pressurize just up to the rating of my lowest pressure relief valve, which was at around 1 psi.
Yeah, you
This,
don't
of
want to
course,
make a
wasn't
bomb.
actually very much pressure, but it should have been enough to keep out any air or moisture, and at this point, it should have been good to go, so I turned on the compressor. And that's it.
And that familiar pumping sound
Now,
once again.
at least in theory, all I had to do was just leave it like this, and if it went anything like my earlier test, it would eventually start generating some liquid nitrogen. I also knew that this was going to take a while to happen, especially because this time, it was first going to have to cool down
explosion.
this huge dewar. However, despite knowing this, over the next few hours, I still slowly got more and more concerned when I didn't see anything condensing, and I genuinely started
In a couple
worrying
hours? That is a
maybe
little
the dewar
concerning.
was in fact trash, or that maybe I'd somehow messed up the cryo cooler or the compressor while I was putting it all back together. It turned out, though, that I was mostly just really impatient and freaking out for no reason, because it wasn't too long after this that I started seeing the first drops of some beautiful liquid nitrogen.
Little bits of rain inside of the drum.
It's actually condensing it.
I still legitimately want to know what his electricity bill is like
Then,
after
only
this.
An hour later, it was
It's probably
basically
very
raining
high.
liquid nitrogen in there, which was really exciting to see, and I thought that it was kind of satisfying to watch it all fall and crash on the bottom of the dewar.
Hey, that's me. That's my
At
name.
the same time, though, I couldn't help but get kind of concerned when I noticed that none of it was collecting, and it seemed like it was all just instantly boiling off.
Well, no, that
What
makes
also
sense, because
really
the metal's
didn't
not
help
cold.
was that this didn't seem to change even after an hour of waiting, and this made me really worry again that the dewar might have actually been non-functional or something, where if that were the case, it would have never been able to collect anything.
You didn't really
Long
pre-chill
story
it, so
short,
it's
though,
just...
I was,
it was
again,
warm.
just really impatient, because it wasn't too long after this that a pool of it started forming at the bottom, which was really relieving to see.
Yes! It's finally collecting something!
It is certainly remarkable how much setup or lead time goes into this, of not only having to flush out the chamber, the dewar with nitrogen, so you gotta wait until that's all replaced. Then you have to wait for the cryo pump to actually get cold enough to start condensing the liquid, the gaseous nitrogen in there. And then once the gaseous nitrogen starts condensing, well, then you have to wait for the gaseous nitrogen to cool down the inside of the dewar, which is probably at room temperature. And that's still a good bit of energy that has to go away. Not to mention the fact that it's a large dewar, so there's a lot of mass. Even if metal's conductive and doesn't take that much energy to cool down by 1 degree of Kelvin, it's still a lot of mass to have to cool down. So you have 3 sources of strong lead time here, making this take a very long time to actually get ready. It's something that would probably take an entire workday to just make sure is happening correctly if this was your job to set one of these up and get it online.
This pool then grew relatively quickly, where only several hours later, I already had what looked like a decent amount, and at this point, I was feeling pretty excited.
Also, you can kind of, the fact that it's kind of wavering like that is not only just due to, the condensation and, droplets falling into it, but because, it is still unstable. Liquid nitrogen needs to be cold, otherwise it's going to just boil off into nitrogen gas again. And so it is kind of slightly boiling at all times. It always has that boiling motion going on to it. Because we do not live in a world that is hospitable to liquid nitrogen being stable.
Okay, there's a good amount there. I mean, it's going now.
The only unfortunate part was that it wasn't too long after this when I looked over at the pressure gauge and I noticed that it was at 0 instead of 1, which told me that the cryocooler wasn't getting nearly enough gas. So I looked over at the nitrogen generator to see what was happening, and I noticed that the flow meter was apparently maxed out with a reading of nearly 6 liters per minute, which wasn't exactly ideal. This was because this nitrogen generator was only able to provide pure nitrogen at up to 4 liters per minute, and this meant that the gas coming over now was contaminated with oxygen and water.
Oh, that's not
The
good.
exact level of contamination was also completely unknown, but as far as I could tell, it most likely wasn't that bad, and the nitrogen purity was still probably above 95%. In my opinion, this was something that I was able to tolerate for this first run, so I decided to just leave it like this.
Fair
but
enough.
In general, this was definitely something that I would have to address later on. With that being said,
Especially given the fact that, as alluded to previously, liquid oxygen is like a notoriously explosive material. Like, you tend not to want to have any liquid oxygen condense. I mean, when it's dilute in liquid nitrogen, it's not really that bad, but given that usually, say, if you had a boil-off event where all the liquid nitrogen boiled off first because it has a slightly higher boiling point, lower boiling point than liquid air, you could have than liquid oxygen, you could have just a pile of liquid oxygen at the bottom, and like that would explode on contact with almost anything, including, metal.
though, over the next day or so, the liquid level then just continued increasing, and it slowly got hazier and hazier because of the water making it past the nitrogen generator. I was then eventually able to fill the entire bottom part, which was really exciting because this should have been about 30 liters, and when this happened, I decided to turn everything off. This was mostly because at this point, it was pretty clear that the system did in fact work, but also, it was because what I had now was more than enough for the one last and very important thing that I still had to test.
Smash a
This,
banana
of
with
course,
it.
was to see if that siphon tube that I'd put in earlier would
Oh, no.
actually work.
Actual testing.
And whether or not I would actually be able to get any of this liquid nitrogen out of the dewar, where if I couldn't, then, well, it would kind of be a huge disaster. There was only one way to find out, though, so I just got started with it by first attaching this large insulated extraction hose that I'd gotten on eBay for a really good price.
Only $800.
Then after that, I just cranked up the nitrogen flow even more, and I blocked
This project
the 1
couldn't get any
PSI
more
relief
expensive.
valve, and the goal was to slowly increase the pressure inside the dewar. While I was waiting for it to increase, I also added a bowl, and I went and changed into some proper protection, which included some sealed boots and a face shield, because I was honestly a bit worried that this whole system might explode. This was because
Well, also you don't want it splashing on yourself
raising
either.
the pressure by maybe several psi, I had no idea if this dewar was actually rated to take any pressure at all, and when I had asked the company that made it, they didn't recommend it.
I mean, it's gotta be rated to take some pressure. It said it was sold for liquid helium, so like,
More specifically, they said that they didn't necessarily design their dewars to have much more than maybe 5 psi in the reservoir, which really did not inspire confidence, especially with a second-hand 30-year-old dewar.
Yeah.
With that in mind, though,
Maybe
I
it's
just let
not
the
the
pressure
best, but
slowly
still
climb,
they was in good
and when
condition.
it eventually got to around 2 psi, I decided to try opening the siphon, and I was expecting to hear something or to see some cold vapor coming out, except literally nothing happened.
Oh, that's scary.
This told me that the pressure was likely still too low, and that I was going to have to push it a little more, which I wasn't exactly excited about. I didn't really have a choice, though, so I just
The good news
closed
is
the
that you'll
valve
hear
and I let it
strong
climb,
hissing before
and
just
as
an
it
actual
increased,
explosion.
I slowly got more and more nervous. Then, when it eventually got to a little over 4 without exploding, I felt that this had to be good enough, and I opened the valve again. This time, I was also instantly greeted with a kind of horrible whistling noise, which told me that the liquid nitrogen was actually moving up the siphon tube. Then, not too long after, I started seeing some nice and cold vapors coming out, and I was really hoping that I would soon get an amazing rush of liquid nitrogen that would just spray out the end of the hose. However, that unfortunately did not happen at all.
Maybe not a glorious spray, more like a...
And it wasn't nearly as impressive as I had
incontinent
imagined.
dribble.
I guess on the positive side, though, it was actually coming out, which told me that the siphon tube was working, and it did kind of speed up over the next few minutes. I was then eventually able to fill this entire bowl with liquid nitrogen, which was about 3.5 liters, and when I saw this,
it only took me 40 minutes.
Pretty excited. This was because finally, after working for what felt like forever on this project, I actually had a bunch of my own homemade liquid nitrogen sitting right in front of me.
Now, Nile,
what also made things
don't
even
step
more
away,
exciting
otherwise...
was that this was only a fraction.
Okay, that's a stupid idea. But I'm betting the funny thing that's going to happen here is that he totally forgets about the fact that the pressure is going to still be building in that dewar while he's not looking at it because he hasn't done anything extra to set it up to make sure it doesn't, get too much higher. And it's going to be like, well, it turns out that it actually can go above 5 psi without exploding. But this was pure luck, and I nearly died. Also, speaking of nearly dying, he is playing with his liquid nitrogen way too much. You should never, ever be doing something like this. Let me see if I can't get the frame. Yeah, even, yes, hypothetically, for a moment, you can, in fact, put your fingers, dip it in liquid nitrogen because of the Leidenfrost effect, where it will, the body heat coming off of your fingers will boil, the small gas pocket around your fingers that insulates you from the rest of the liquid nitrogen. But that really only works for, a fraction of a second. If you kept it there, it would, in fact, not be working very much so. The Mythbusters actually exemplified this on the other side of the coin of heat, where they tested a myth where if you doused your hands in water and then very quickly dipped your hand in and out of a pot of molten lead, you would not get burned. And yeah, no, it's true. It's just not something I would ever want to try. There are things that work in theory that do also work in practice, but I would never, ever, ever want to try to make work in practice. But yes, liquid nitrogen is fun for the whole family until you end up freezing somebody and, well, nobody wants that funeral. This also seems like a good time for me to mention a story where, researchers do actually love playing with this stuff. When I was in graduate school, thankfully I don't think any of my fellow graduate students actually did this, but they told me stories of how they knew former grad students because, their senior, the people above them had graduated and now they were the people above me. So the people they used to know in grad school, they used to basically play a form of chicken with liquid nitrogen, in the sense of they would pour a bunch of liquid nitrogen over a wooden chair or a plastic chair or something that wasn't super conductive of heat, but still you could get really cold without shattering. And then they would see who could sit longest bare-assed on the chair before having to, squeal and get up because of how fucking cold the chair is. Graduate students are not immune to being stupid. They will do stuff like this for fun and entertainment. I would never do something like that because why? Why am I going to risk ripping off shards of my butt skin? That doesn't sound like a good time. Maybe it just makes me the ultimate chicken, but Ultimate Chicken gets to go home with all of his cells intact.
Only a fraction of what was still in the dewar, and I felt that I had to celebrate this by freezing something.
What? Oh my god, he's testing it so
The first thing that I
much.
came across was this
Ludicrous.
old orange. I then patiently waited for it to fully solidify, and I spent the next several minutes having way too much fun smashing it and turning it into a crunchy orange dust.
He never thinks about how he has to
When I was
clean this up
eventually done
afterwards.
celebrating, though, I quickly cleaned up my huge mess, and I started draining all of the remaining liquid nitrogen into an empty 30-liter dewar. I was then able to completely empty out everything that I'd made, which nearly filled this entire dewar, and at this point, I was feeling pretty good about my setup. This was because overall, it clearly worked, and on top of that, I was actually able to make a decent amount of liquid nitrogen at a rate of about 0.58 liters an hour, or around 14 liters a day. This was also way better than
It's acceptable for somebody like him that only needs to use it in moderate batches. That is unacceptably slow for research needs. We would need in like graduate school like to fill up a dewar bigger than the giant one in the background like once every week, and several labs would need to do this. 14 liters a day would never be able to supply that.
ever expected for my first run,
so good.
where it was already kind of
Very
close
impressive.
to the 20 liters a day advertised by those Chinese systems, and honestly, I was really tempted to say this was good enough.
However,
at the same time, there were just way too many glaring problems that I couldn't let go of, like the fact that the liquid nitrogen was being heavily contaminated by oxygen and water vapor, and that the extraction system was almost comically slow. There were also some other major things that I really didn't like about the system in general, especially the fact that I still wasn't even close to maxing out the cryocooler, and I felt that I had to do some final fixes.
What did it say? I didn't quite process the sentence that was said there. The whole system was under a vacuum because the cryocooler was condensing way more nitrogen than it was being provided. Oh, okay. So like, yeah, the actual inner storage system is at too low of pressure because, yeah, the dinky little nitrogen tube feeding into a nitrogen filter tube air compressor thingy feeding into it was just not enough for this this thirsty beast of an instrument.
Cryocooler, and I felt that I had to do some final fixes. So again, I ended up taking the whole thing apart, and I immediately started working on all of the random changes that I wanted to do. And after about a month of effort, this was what I ended up with, where for the most part, it still kind of looked the same. However, there were some pretty
That's a much bigger
upgrades
tube on the right
where
there.
the
Wow.
nitrogen generator was now massive, and everything on top of the dewar was rearranged, and a few extra things were added. When I tested it out, it was also...
Hold on, how many extra things got added? So let's see, that's the better nitrogen input that we just noticed, the big tube, dedicated pressure gauge hole. Okay, instead of having to go through something else. Simplified extraction system, if you say so. A powerful flashlight instead of some dinky LEDs. And of course, the camera. So that way we can get a good shot for his video.
Things were added. When I tested it out, it was also very obvious that it was way better than before, where the first thing that I noticed was that it was producing a lot more liquid nitrogen. In fact, it was actually making over 1 liter an hour, which was nearly twice as fast as it was before.
24 liters a day.
And honestly, way better than I ever imagined. And at this point, I was definitely maxing out the cryocooler. At the same time, everything that I was making was crystal clear with no sign of fogging or haziness, and over a few days, I was actually able to collect nearly 100 liters of beautiful liquid nitrogen, which was the obscene amount that I only dreamed of making when I first started this project. I should also say...
God, that's like, that's just, again, the chemist's dream of being able to have just all of these extremely useful but extremely dangerous chemicals just lying around in case you ever decide to have a use for them or you just want to dick around with them a little bit. I'm so envious. But I also don't have $20,000 in engineering expertise, so good for him.
That this was all only possible thanks to this completely new and massive nitrogen generator that I'd put together, which was able to output around 7 times more nitrogen gas than the old one. What was probably my favorite upgrade, though, was swapping out the simple sight glass for this new probe lens and phone setup, which, along with this new powerful flashlight at the back, allowed me to easily see inside and to record this way higher quality video. It also allowed me to easily monitor the liquid nitrogen level remotely from my computer, which may or may not be a bit overkill, but I found it to be pretty useful.
No, I mean, to have that remote kind of system
kind of
is
sad
pretty
part
good.
With this whole new setup, though,
And considering if there's ever a hazard, you don't want to approach it that much.
Which was that despite making the siphon tube way bigger and swapping the extraction hose to one with a much higher flow rate, it still didn't end up blasting out like the fire hose that I was hoping for.
I wonder if his decision to actually make the diameter tube inside of it bigger was actually a bad idea. I mean, yes, theoretically, you had enough pressure to push enough gas pressure in the tank to actually push the liquid nitrogen out effectively, then yeah, that would mean more liquid coming up the tube and out through the nozzle at the end there. But if you don't have that much pressure, then a larger diameter tube is just going to make it harder to actually push that liquid nitrogen out. If you had a smaller diameter tube, it would just, be a little easier to push out. You'd have a much smaller surface area to like push upwards upon. So I wonder if that actually backfired on him there. I mean, it's still working better than it was before, but
I mean,
it usually takes
it
some
was
time.
Definitely way faster than before, where I was
have
actually able
the
to
end
fill
has
this
to cool down
entire
too.
bowl in around 2 minutes, which was so much better than the nearly 12 minutes that it took last time. When I did a side-by-side comparing the two, the difference was also super obvious, and for the most part, I'm happy with how it is now. Overall, I was also very happy with how this entire project had turned out, and after transferring all of the liquid nitrogen to my 30-liter dewar, as well as to a new 60-liter dewar, I finally felt that I was done. This was because, at this point, I had successfully put together a huge liquid nitrogen generator that actually outperformed the Chinese systems that I was originally looking at, and that at least technically did end up being cheaper.
Yeah, $500. Just had to put in about, maybe 160 billable hours of labor in order to save that $500. Good on ya. It's still really impressive just to be able to say, yeah, I made my own liquid nitrogen condensing system. Like, no big ish. That's cool, though. Let's see, compared to 24-liter a day system, probably saved a few thousand. Yeah, I guess in that sense, in outperforming the cheapest ones. However, that's not considering the time, pain, and effort it took. Yup, along with all the stuff you already owned, like the turbo pump, the air compressor, the vacuum gauge, etc., and the water cooler. On a side note, I found out much later on that a new cryo cooler compressor can be purchased for $10,000 from Sumitomo. So it could have saved a lot if I had actually gotten a good deal. Oops.
At the same time, it was also basically able to do everything that I wanted.
Yeah, also, we didn't even count in how much you spent in electricity, too. That's probably a big component of this, because this is not a trivial amount of electricity, given that you have to power the pump and use it to move the water cooling around, and there's just a lot of power supply going into this. Like, this is not an energy negligible process.
And dreamed of.
Thanks for reminding me of that.
Storing 100 liters at a time, and there really wasn't much else that I wanted to change or fix. I mean, besides the slight problem that there did end up being a small leak in the dewar, which means that every time that I want to run the system, I'm gonna have to run the vacuum pump at the same time. And while this is mostly just a minor inconvenience, I should probably try and fix this in the future. Until then, though, I'm just going to focus on the fact that from this point on, I can officially use only my own homemade liquid nitrogen for all of my future projects. In my opinion, this is also really exciting, especially because I have a bunch of really interesting projects lined up, like that entire Air series that I mentioned earlier, as well as a couple that I'm not ready to talk about yet.
It's so bright. What is this?
What I'm probably most excited about, though, is that this now puts me one step closer to my dream of recreating this superconductor demo that I did years ago, except with only things that I've made. At the time, only the superconductor and the ferrofluid were mine, but now I could add liquid nitrogen to the list, and this meant that the only things left to make were the glass dish and the magnet, both of which I'm currently working on.
A bit.
I'm also hoping that I'll be
bit
able
eccentric,
to finish
but
all
you
of
know,
this by next
fair.
year.
We all have our
and
goals.
that it won't be too horribly expensive, but if it is, I should still be okay thanks to all of my amazing YouTube members and patrons, and because of Brilliant.
All right, now we're into the sponsored segment, but anyways, Val, cool video. It's a little less chemistry. I guess I should have expected that. It's a lot more physics and engineering, but so I had less to maybe explain and yap about, but I already did plenty of that in the Nobel Prize video. Entertaining stuff as always. I can't say I've ever seen anybody assemble a home liquid nitrogen setup, especially one that efficient, or the inside of a liquid nitrogen doer as it's actually condensing the liquid nitrogen. So, as usual, very good work done by Sir Nigel of Red. And I thank you for being here and watching the video with me and watching me yap about the video a little bit. Hopefully, I provided some interesting additional entertainment and insight to what was going on. And you enjoyed your time here. If you enjoyed the videos that I watched today, I'd recommend that you go to those videos and leave them a like. If you enjoyed my video, I'd recommend that you leave that a like as well. Share it with people you know, and subscribe if you haven't subscribed already. If you want to join the Discord, there's also a Discord down below. You're welcome to join that link. We talk mostly video games, but I'm down to talk science basically anytime. Next week is Thanksgiving week, so I won't be planning on doing anything on Thursday. I'll be enjoying my day off from work. Not that I'm not enjoying myself here, but, you know, I'd like to maybe take myself a little bit of a break. On Monday, Tuesday, we will be doing... It would be a rare double Mega Man week. We'll have Mega Man Powered Up returning on Monday, which I need to make a poll for that in the Discord to see what character I'm playing next. And we will be playing a Mega Man ROM hack of Mega Man 1, known as Mega Man Law of Justice, on Tuesday. Never tried it before, but it was I heard about it a while ago through a random little games article, and I've wanted to try it since, and we'll be finally having a time to take a crack at it. So if you're interested in that, stick around. We'll be back next week. And I thank you again for being here and keeping me company while I nerd out about my profession and my special interests. So thank you for joining me. Have a good rest of your night. Enjoy your weekend, and I'll talk to you the next time I see you. Ciao.